Welcome to Study Loop.
This is chapter 21, problem number 84. We're given this figure that consists of a coil and a solenoid inside, as you can see. So the coil has number of turns, it's 190, and the radius of it is 5 centimeters, and it's hooked up to a resistor that has 12 ohms of resistance, and it's surrounding the solenoid that has number of turns per unit length as 230 turns per centimeter though, so it's going to be equal to 10 times 100, right? Because if per centimeter is 230, per meter it's going to be 23,000 turns per meter, right? So the current in the solenoid is changing at a constant rate from 0 to 2 amps within the time interval of 0.1 seconds. So then delta I over delta T across the solenoid is something other than 0, right? It's changing. So 2 minus 0 divided by 0.1 second is 2 over 0.1. So the ratio is 20 amps per second, right? Now, calculate the magnitude and the direction of the induced current in the outer coil. So the change in flux through the solenoid due to the change in current is going to induce EMF on the coil, right? So in order to calculate the magnitude of this EMF induced on the coil, we have number of turns in the coil and the change of rate of change of flux through this coil. Then this flux is going to be generated by the solenoid itself, right? So the cross-sectional area of the solenoid. Let's remember what the magnitude of the magnetic field of a solenoid is if there is current passing through it. So it's mu naught N solenoid times the current through the solenoid divided by the length of the solenoid, right? So we can plug these two equations in the induced EMF equation. Then what we get, let's do it on the next page. So the epsilon then is going to be equal to N coil times the cross-sectional area of the solenoid, dB, which is the magnetic field of the solenoid, divided by dt. And remember, B solenoid, we said that it's equal to mu naught N solenoid, the current through the solenoid divided by L solenoid. So let's put this back in inside the delta. So N coil, A solenoid, D dt. We have mu naught N solenoid, I solenoid divided by L solenoid. Right? Now, these three, mu naught, N sol, and L sol, they are not depending on time. The only thing that is changing with respect to time is the current through the solenoid, right? So we can take these out of delta. So N coil, area of cross-sectional area of the solenoid, mu naught, a number of turns in the solenoid, divided by length of the solenoid, times delta I of solenoid divided by delta T is the EMF across the coil, right? So then, as you know, the coil's EMF from Ohm's law, that equals to the current flowing through the coil times R, right? And this is what we're looking for. We are looking for the current through the coil. So then if I divide both sides by R, then I coil happens to be epsilon over R, which we found epsilon is this, right? N coil, A solenoid, mu naught, N solenoid divided by L solenoid, delta I solenoid over delta T. And now we have R in denominator. So let's see what we know already. First of all, we know N coil. N coil is 190, right? Then the area of the solenoid is going to be pi times R solenoid, right? And our solenoid was given us, again, our solenoid was given as 0.45, pardon me. This is not 0.45, it is 4.5 centimeters. That is going to be equal to 0.045 meters, so that we can put it here, squared, right? The area of the solenoid. Mu naught would be 4 pi times 10 to the power of -7. Well, it's not going to fit in here. Let me carry everything here, okay? Number of turns times the pi times 0.045 squared times mu. The value of mu is this. And then, so forget about this. And then we have number of turns divided by L solenoid, right? This is what we were given. So that was 23,000, right? Divided by R being 12 ohms given to us in the problem. Delta I solenoid over delta T, we had calculated it to be 2 over 0.1, if you will. So then what we find out, the magnitude of the current through the coil to be 5.8 times 10 to the power of -2 amps. Now, this is the magnitude. How are we going to determine the direction of this current? Now, let's look at the current flowing through the solenoid, right? It's going up and then curling around the solenoid itself, and then it comes down. So then flux, the B field generated by the solenoid is actually to the left, right? So then if the B field generated by the solenoid is to the left, so is the flux. But the current is increasing, which means the flux is increasing. Flux through the solenoid is increasing as we go to the left. So the flux to the left through the solenoid is increasing. So what the outer coil is going to want to do is to oppose to that, right? It's going to want to generate an opposing flux through itself. So it's going to want the flux to be in the right direction. If you want the flux to be in the right direction, then the B field has to be in the same direction. And then you can use your right hand rule number 1. If the B field has to be to the right, then the current must be going up. Induced current, direction of the induced current must be from left towards the right side of the resistor that we have. So then the direction is, let me put it here. Direction is from the left of R to the right.